The title is Prototype Using Image Analysis to Control Hardware Crafting for Isotropic Nonwoven Applications. For the major applications in this field, normally we start from mass of fibers and through the cutting process and the cross-cutting we can get a web. This web can be finished by several methods. One of them, most important, is the needling process. Although this is very studied, and for the major application, the system works okay. But we have to have in mind that when you're crossing a web coming from a car, each layer keeps its particular direction. Fiber keeps its particular direction. So we have different directions in different layers of the final web. For many applications, this is not important, but there are applications where this is critical, because if you need a very, very random distribution of the poles, and for other particular technical applications, we have to have an isotropic situation. The project is intended to create those conditions. I think this is slow, no? That's okay. Normally, it's a process like this. We have really a carding and a cross-lecture. There we go. I think so. I hope so. I'm coming. The needling process may be done in two different ways. Just one side, that's an image that is coming now, and both sides. In one operation or two operations. When it is done in two operations, normally the first is the preneedling with the less density of needles, and the second is the final needling with a higher density of needles. The needles are the magic principle of the system. They are special needles, normally with a triangle section in which vertically we have barbs. These barbs takes tufts of fibers from the horizontal position to vertical position and set them inside this system. This will get a structure like this where you can see the holes of the needles and the other fibers going around these holes. It can be seen it's more complex than this because normally we have a dual structure in this. An horizontal structure and a vertical structure. They link together and the excellent mechanical properties of these products come exactly from the frictional forces developed between these two substructures. Commercially, there are lines available, normally composed of a card, a cross clap, and two needling machines. The first one is the preneedling, the second one is the final needling. This is available for normal products in this field. What's the project idea? Is to change this little bit. Because we don't have an isotropic situation, we intend to create it with this system. The idea is to insert, to do the needling into two steps, but inserting between them a drafting operation. With this drafting operation, it is intended that the fibers of the horizontal section may rotate down with the fibers of vertical rotation and reorient themselves. If they are oriented and we change that position, we have to be careful because we can get a new oriented situation. So the critical point of all this is exactly the precise control of the degree of orientation of fibers we can get with the drafting system. Normally, we are using in our lab small lab for a small equipment for this component, lab card, cross lab needling machine. And as I said, the critical point is control. Using a normal system, there are special drafting systems available. We can't control this level. It's impossible to control because the machine is set at the beginning of the process and keeps the settings during all the process. Any small variation affects the isotropic state of the material permanently. So we have to have a special machine to make this drafting, special drafting. And the control has to be dynamic, so we are using an image analysis. The results of the image analysis interfere automatically and online with the processing parameters of the drafting machine. Basically, this is the idea. We have 5 rolls drafting unit with 2 cameras, D, matter D, one in the input, another in the output. The input camera takes a picture, send it to the computer, and the picture is transformed, it's changed into 256 gray levels image. The gray levels are counted by another program, and it calculates an histogram and the distribution. From this distribution, we can use Shannon mechanism, for example, Shannon formula, and get the CV, and get also an important information, which is the entropy of this image. Calculating the entropy at the input and output points, we can rule the machine according to this, taking in accordance that if the entropy increases, this means that the degree of disorder increases also. So, with a low entropy, we have a very horrible state. With a high entropy, we have a very disordered state, which is the case we are interested in, because as the disorder degree increases, we have a more isotropic state. We are more near that position. The prototype is already working in our lab. This is the image. We have 5 motors, 5 variable frequency motors, holding the lower holes. The upper holes are pressed with pneumatic systems, and in this prototype we can change the speed of each one of the holes. We can change the pressure of the upper holes, and we can change the position of the 3 inside holes. The first and the last are fixed. The other 3 can move, and we can increase or decrease the field of the drafting. This is very important because sometimes it can affect the way the drafting is done. This is the front view. Right, to validate this method, we used the following. Sample have been drafted two different levels with a system composed of a video camera and a computer system. We collect the image and treated them in described order, and we calculated the entropy of first order of both images, before and after. This is the image system. Before drafting, the image has been analyzed, as I said, and all the values were calculated. And we got, this is the image on cover, this is the image after treatment to get 256 gray levels image. And the gray distribution in this one, with the standard deviation 20.68 and an entropy of 6.363. After 10% of drafting, again image, and conversion, and an increase in standard deviation and the entropy value. 30% drafting, and another increase. So as we increase the drafting level, the entropy increases also. Because there is a moment where it will increase. That's the critical point we want to reach. In the machine, we shall have a computer running all the process, and this computer has a special algorithm that will account for the value of variation of the entropy and takes the better point of the entropy for each moment at each moment. It's an online system and working with the real data coming from the system. And it's an intelligent algorithm that adapts automatically of each situation. This is the result, and this is the Shannon conformism we use to calculate the entropy, using the probability of each gray level. Indirect confirmation. To be sure about the system, we have to have another method to check out if we are right or not. Using a thermal press, we took transparent replicas from the surface of the samples in 3 states and treat them in a laser diffraction bank. In this bank, I'm sorry, it's very slow. There you go, this is the scan. We have a laser beam, the sample, collimating lens, and we get a diffraction image. This is getting a bunch like this, and the diffraction image can change, can vary between 2 extreme positions. It can be a circle or an ellipsis. If the diffraction image is a circle, this means that there is no any preferential direction in the fibers. If there is any preferential direction in the fibers, you can get an ellipsis. And this ellipsis can be, the 2 axes of the ellipsis can be measured. We have a special program that measures automatically the greater and the smaller axis, makes the ratio between them and determines what we call the ellipticity of this ellipsis. This is a direct measurement of the degree of order, disorder matter of the system and the sample. Here are the images. On the right one, it's not can be very well seen, but the computer makes automatically a contour of the image, which is the most important part of information to avoid noise, and calculates automatically if it's a circle or not, because if it's a circle, the both axes must be equal and the ratio must be 1. When it is greater than 1, it means that it is an axis. Using this value of ellipticity, it's mathematical possible to calculate a degree of order and run the machine in the best condition possible. Well, I think that's all. Thank you very much. My apologies.
Are there any questions for the speaker?
Thank you for your presentation. So I would like to ask about the prototype. After you make the web with needle punching, you put it in this machine and you have to take some photos for the product?
Yes.
And what about the cylinders, 5 cylinders? So you
I'm sorry, I didn't follow you. What about the
some drafting cylinders in the prototype machine. So you build the fabric after the needle punching, and you start to take some photos for it.
Yes.
So you change the speed for each draft, or
Yes. Yes, the drafting is done in 4 different stages with 5 rolls. We have 4 different zones, and the zones have different levels of drafting. Normally they start with a very little value of increase along the time, just to get uniformity, not to lose uniformity of the web. Is this a question or am I wrong?
yes, and I would like to ask about the 3 layers in the beginning. You put just 3 layers.
3 layers?
3 layers for the web to get the final.
That's just an example.
An example.
Yeah,
It's not the
it
experiment.
doesn't mean that we only use 3 layers.
Uh-huh.
It depends what the mass you want for Unitarian.
Okay, thank you.
No.
We have time for one more question. Anyone else? Thank you very much.